Good afternoon, sir. Participants are yet to come, so we can wait for 2 more minutes.
Sure, ma'am. Sure, ma'am. Sure.
Rajun sir, you are working with Jyoti Engineering College, right? Rajun sir, you are working with Jyoti Engineering College. Oh, good.
Yes.
Okay. EC, right?
Easy department.
Okay.
Okay, we can begin the session. CP Miss, over to you.
Okay. To session 8 of faculty development program organized by Department of Electronics and Communication Engineering, Jyoti Engineering College. Let me introduce our resource person for today, Dr. Anand of Electronics and Communication Engineering at the Indian Institute of Information Technology, Kottayam. With a strong expertise in advanced wireless communication systems and emerging 6G technologies, his research focus include reconfigurable intelligent surfaces, a transformative technology expected to redefine how wireless signals are shaped and directed in the next generation networks. As a senior faculty member at a leading national institution, Dr. Anand brings both research depth and academic leadership to the FDP, providing participants with cutting edge insights into intelligent surface assisted communication architectures. We are honored to invite Dr. Anand A. to deliver an online session on Reconfigurable Intelligent Surfaces Assisted Communication at our faculty development program on Advanced Communication Systems, the Department of Electronics and Communication Engineering of Jyoti Engineering College, Chirudurthi. We warmly welcome you, sir, for your gracious online presence and valuable insight to our faculty community. Welcome, sir.
Thank you, ma'am. Thank you for the nice introduction. So thank you to the coordinators of this FDP and the administration of Jyoti Engineering College for giving me this wonderful opportunity to share my knowledge on the reconfigurable intelligent surface assisted technique, because I have done some works on reconfigurable intelligent surface assisted communication, and we have presented our paper in some reputed conferences. So I'll be sharing that work. Okay, so before proceeding with the presentation, I hope all of you are able to see the screen.
Yes, sir.
Yes, sir. Yes.
Okay. So under this reconfigurable intelligent surface assisted communication, I would like to discuss about a low complexity detector for RAS assisted single input multiple output system. So this is work by my undergraduate student, Mr. Jashwant Kumar, along with my PhD scholar, Ms. Annette James. So before getting into my presentation, I just want to, say a few words about our institute at IIIT Kottayam. So our institute is located at Pala, Kottayam, and it was established in the year around 2015. And we have several undergraduate, postgraduate, and PhD programs offered by various departments like electronics and communication engineering, computer science and engineering, computer science and engineering with cyber security, computer science and engineering with AI and data science, and so on. So this is the view of our institute during a rainy season. So there were no, edits to the photo which was taken. And coming to the research group which I work, so we have a research group called Next Generation Communications Research Group at our institute. So we have a good number of faculty members who work on various cutting edge research, especially like, 6G wireless technologies on waveform design, like orthogonal time frequency space, affine frequency division multiplexing, then reconfigurable intelligent surface, wireless body area network, optical wireless communication, and so on. Along with that, our faculty members also guide several PhD students and internships for various UG students of nearby or students from other states as well. And we also organize various FDPs, SDTPs, and workshops during the summer break as well as winter break. And we have an upcoming FDP or STTP in the next week, so which is a recent trends in wireless communication technologies for beyond the 5G systems. So we have both online as well as offline participations. Okay, so those who are interested to know much more about the technologies that may support beyond 5G systems can register for this workshop or STTP. So coming to our department, we have a good team of faculty members working under different diverse fields of electronics and communication engineering, ranging from analog electronics, VLSI, image processing, signal processing, then communication, RF and microwave antenna design, embedded systems, and so on. And we also are going to organize a conference called iSense, which is International Conference on Smart Electronics and Communication Systems 2026. And we are conducting this conference by December 11 and 12. And all the accepted papers and the presented one will be submitted to IEEE Expo. By default, it is becoming an Scopus index. And right now we have the first deadline for our conference paper submission, which is June 15, so which gets over by Monday. So we have planned to extend it with a hard deadline of June 30th. So any faculty member or researcher who are having some work which has to be submitted to conference, please, we warmly welcome you to submit to our conference, so which can be visited from this website. And coming to our department, so we have several programs. So one such is our PhD program, and we also undertake several PhD students every twice in a year. So during August intake as well as January intake we have. So about that also you can find in this website. Okay, so coming to the outline of my presentation, first I will give you a small introduction to Reconfigurable Intelligent Surface. Followed by that, what are the ways this Reconfigurable Intelligent Surface can be used in communication system to support the requirements. And two such examples of the use case of RIS. One is a reflector and another one is access point. I will show the system model and some performance analysis which we have done in terms of simulation results. And finally, after this, I will give another presentation on how to develop a low complexity detector, or what are the ways we have deployed or undergone to have a low complexity detector for a such RIS assisted communication system integrating single input multiple output system. Okay, so coming to the introduction, so these are all the basic requirements of our wireless communication system. So our basic requirements, or one is we expect higher data rate, and again it changes or increases with respect to every generations of mobile communication. So especially if you take 5G, the expected peak data rate is 20 gigabits per second. Similar way, if you take any optical fiber communication, so which is governed by DOCSIS, so the maximum data rate expected is 10 gigabits per second. So this is one aspect of our requirement towards wireless communication. Similar way, we also expect low error probability or low error rate, so which can be measured in terms of bit error rate or symbol error rate or outage probability. So especially if you take a bit error rate for a successful transmission over wireless communication, if it is voice, the expected one is 10 to the power minus 3. So this means that out of 1000 bits, we are okay to have 1 bit in error. Similar way, if you take any digital data, okay, so which may be an image or otherwise a file or a data. So for that, the tolerable amount of BR is 10 to the power minus 6. So which means if you transmit 10 to the power 6 number of bits, out of which 1 bit can be in error. So now you can understand that, especially with respect to reliability, we are very stringent with our communication system such that it has to be more reliable. And on the other side, if you see, we have few more other requirements. So one is a connectivity and coverage. So this means that wherever you go, the network operator has to provide you a good amount of signal strength so that you can communicate either through data or otherwise voice and so on. Similar way, we have another requirement which is low computational complexity. So this is very crucial because whenever you develop some system, you cannot say that we can have higher computation complexity involved. The reason is that if suppose we are having more and more amount of computations involved, then again the more and more amount of energy is getting dissipated. So this will make sure that you need to charge your device more often than what we are trying to do. So these are all some basic communication system requirements. So apart from that, we have some constraint like energy efficiency, okay, and so on. So there are several requirements. So these are all some basic requirements. So our work in this presentation will focus on two things. One is trying to achieve a good reliability, that means high reliability or less error rate, and second one is to address the computational complexity involved. Okay, so these are the two things our system will address from the requirements of wireless communication systems. Okay, so are there any doubts? So participants, if you have any doubts, you can feel free to interact with me. So there are something. So if there are any questions, please you can ask me. Okay. Okay, so coming to Reconfigurable Intelligent Surface. Okay, so it is an artificially made surface which has the ability to, change the nature of the electromagnetic radiations or waves that is getting impinged on that surface. Okay, so that's what the reconfigurable intelligent surface is. And again, it is called as intelligent because it can be controlled by either turning on and off of that particular element. So again, if you say a reconfigurable intelligent surface, it is a it is composed of several elements of a minute metamaterial element. Okay, and all these elements can be powered by using a PIN diode. Okay, PIN diode. So you can see the structure here. You can see this is one element. Okay, this is one element which is powered by a bias. Okay, which is powered by a bias. And again, this can be activated by using this PIN diode. Okay, that is on and off of this element can be done using this PIN diode, such that on and off will have a different characteristics. Okay, by which your electromagnetic wave will react to this, RIS surface. Okay, so this is how the structure will look like. And again, there are several types of hardware under this RIS. One is active RIS, and the second one is passive, and the third one is hybrid. So if it is active, it means that this reflective surface is connected with some, high power or high energy device, such that it can perform several tasks. Okay, so it's like, you have some, see, earlier days we were having some relays under cooperative communication systems with wireless communication. So one such example for cooperative communication is our mobile phone hotspot. Okay, so if suppose we do not have a network or otherwise data connectivity, so what we request our colleague is that we will ask for a Wi-Fi hotspot, so that that person who is providing our Wi-Fi hotspot device will act as a relay, and our device will act as a destination, and so on. So you can see that in that scenario, the relay will provide some amount of energy to the system, and it makes a communication seemingly possible from one end to the other end. The same way, if it is active, this RIS surfaces will be backed by some power source, and it can operate under different modes. Okay, so that's what with active. Whereas if it is passive, your RIS surface will only act as a reflector. Okay, so it doesn't have high power source backed by its. So due to that, it'll just act like a mirror, and whatever the electromagnetic wave which is getting struck on the surface will get reflected towards a particular direction. And again, if you want to change the orientation or the angle at which this reflection has to reach, then we have to adjust it based on the activation of each RIS element. So that's what the key principle that can be done here. Similarly, we have a hybrid, which indicates that we will have some portion of our RIS element, RIS surface, which are active, and some portion of our RIS surface will be passive. So that's what our hybrid. So coming to the different modes of operation, so it can perform several modes. So one is it can perform reflection. So mere reflection, like whatever the electromagnetic waves, it falls on the reflecting surface, it gets reflected to certain direction. Similar way, it can also perform refraction, and it can also perform absorption, and it can perform focusing, and so on. So according to all these modes of operation of RIS, it can be used in different applications. See, for an example, if we have some blockage between the source and destination. So what we can do is, like, we can have a reconfigurable intelligent surface in between the source and destination, so that this reconfigurable intelligent surface can reflect all the waves that get struck towards a particular location where the destination is. So, to avoid blockage, we can use RIS as a reflection. Okay, reflecting mode. Similar way, if suppose we are inside a room and we expect a good coverage or connectivity with a good signal strength. So what we can do is, we can have this reconfigurable intelligent surface mounted on the window, so along with the glass, so that whatever the electromagnetic waves which are falling on this reconfigurable intelligent surface can get through the window, and it can provide service to those users who are present inside the building. Because as you know that as the generations are increasing, when we are trying to move from lower frequency to higher frequency, the problem that we get is the signals were not able to propagate over longer distance. And again, those signals are getting very much attenuated or attenuated severely because of, even small blockages, walls and so on. Okay, so these things can be avoided using refraction. The other one is, about absorption. See, for an example, we have certain area in which this electromagnetic radiation should not get through. Okay, so in those cases, what we can do is like we can put an RIS surface, okay, mounted on either a building or wall, such that this RIS will observe all the electromagnetic radiation that falls on that. Okay, so similar way we can perform focusing, polarization, splitting, analog processing, and so on. So coming to the advantages of RIS, okay. So as I told earlier, we were having some technique to provide coverage or to provide a proper signal strength where there is some blockage. Okay, so one such technique is our relaying technique. Okay, again, you can do relay using a single transmit antenna, or otherwise you can perform using multiple transmit antenna. So that's what this scheme you can see, relay and MIMO relay. So the problem with this relay and MIMO relay is that, see, there is a device which has to be powered and it requires high amount of energy. Okay, or otherwise it needs high amount of power to be consumed over some time. Because this relay may again operate under two modes. Either it may act as, amplify and forward mode, or otherwise it is going to serve as decode and forward. So in both these cases, it has to do some sort of signal processing, which may consume some amount of energy. Okay. Whereas if we incorporate reconfigurable intelligent surface, which doesn't need any power source, as a reflector medium, what we can do is like we can attain the same, principle of, getting the signal through a dense blockage area to the particular destination. So this is one very good, application of RIS, or, benefit of RIS. Okay. So similar way, we have something called, backscatter. Again, RIS outperform almost all of these techniques compared to the existing one. Okay. So are there any questions based on the things we have discussed? Yes, if there are any queries, please, you can either type in the chat box, or others, you can feel free to interact with me so that I can share my, ideas or, things. Okay, so next, coming to, RIS standardization timeline, we have 3GPP, so which takes care of, mobile communication, okay, standardization body. Similar way, they started exploring, RIS as one of an element for our upcoming generations, like, 6G. And this is what the timeline. Okay. So, this RIS started the, initial shape or research in the year around, 2014 to 15. Okay. So, and after that, maybe around 2020 onwards, we can see that, certain, several industries, okay, they started developing prototyping, or others, developing some reconfigurable intelligence assisted surfaces. And, they started developing some research. Okay. So around 2015, we were having only, theoretical research, whereas by 2020 onwards, we started having, deployment based, okay, RIS research. And, maybe for the upcoming 6G, we may expect, or we can see, RIS coming into shape, and may also, acquire some part of 6G. So coming to the use cases, there are several use cases of RIS. Okay, so here you can see an scenario, okay, on the right hand side. So you have a drone, okay, and you have, certain number of users, okay, who are grouped here, and you have two buildings, okay. So initially assume that, both the buildings are there, and there is no RIS surface on this building, okay. And assume that these users are in some location where they were not able to, get any proper signal, okay, because of, some blockage. So what we can do is like we can use unmanned aerial vehicle, and we can provide coverage. Okay, so that is one classical example for providing, connectivity or coverage to certain users group. Okay. Again, when you are using this kind of unmanned aerial vehicle, what you can see is there may be some other blockage. So that's what you can see. This building, if it is providing some blockage, what we can do is we can have an RIS surface installed, okay, on some building wall. So you can have this connection or this connectivity through this reflection from this unmanned aerial vehicle to this particular group user. So what we can do is like we can integrate this RIS along with unmanned aerial vehicle communication, or otherwise with the conventional, communication. So this is one thing. Second one is you can see that, RIS can serve as a physical layer security, in the sense, see, if there are some eavesdropper, okay, along the channel of the intended communication links. So this eavesdropper will be trying to tap the information associated between those two users. So in those cases, what we can do is like, again, here also we can use RIS such that this RIS can provide some phase deflected signal to the eavesdropper along with this direct line of sight communication between the source. So that if this overhearing signals which comes directly from your base station and this reflected signal which comes from your RIS or 180-degree out of phase, we can make sure that, this eavesdropper will never get any information about this, signal that is intended for this group of users. So such kind of physical layer security also can be established using this RIS. So one such classical example, see, let us assume you have a sinusoidal wave and you want to transmit the sinusoidal wave from one distance to the other distance. And again, the sinusoidal wave will reach the destination with some slight delay because of the distance between the transmitter and receiver. Now assume you have another path which is taken by the signal that you are transmitting. And if it is 180-degree out of phase, what happens is that you will never get any information. Okay. So this is one huge challenge in our communication. So that's the reason we primarily focus on, phase synchronization of, the signal that we receive. So if we were able to establish such 180-degree out of phase with the help of RIS, what we can ensure is this eavesdropper will get only a null signal. Okay. Which means that, the sum of this overhearing signals directly from the base station and this 180-degree out of phase signal will cancel each other so that, it won't get any information. So it can be used for physical layer security. The next, it can also be used for, millimeter wave communication. As we know, see, millimeter wave communication usually operates at higher frequency. So there are some challenge with respect to blockage. In the sense, even if we have a thin wall, these millimeter waves cannot propagate through that. Okay. The same thing applies for, dense foliage or other, dense forest. So you can see a tree-shaped structure. So which is initially obstructing the signal path between the base station and the user group. So in such scenarios, what we can do is like we can have some reflecting surface installed or mounted on some wall. So this reflection from this reconfigurable intelligent surface can, ensure that these group of users were having a signal information. Okay. Similar way, RIS also can be used along with, SWIFT technique, which is simultaneous wireless information and power transfer. So we all know that, this is an energy harvesting technique used in wireless communication system, where to sustainably run this wireless communication device, we go for energy harvesting. Okay. That means, so whenever it receives some signal, okay, there are again several types of, SWIFT technique based on, power division rule, then based on, time splitting and so on. Okay. So especially if you take, power splitting, what happens is that, okay, whenever your receiver antenna receives, certain received signal with received power, it divides it into two parts. One is for energy harvesting path, another one is for, signal decoding path. The similar kind of activity can also be done using, RIS. Like, anyway, we know that RIS is going to reflect the signal just by intending certain reflected signals towards particular direction. And if the devices which are located in some area or, having very less amount of energy, we can direct some energy towards those things. Okay, so that's what this idea, RIS assisted SWIFT and so on. Similar way, we can also use for, D2D, device to device communication. Okay, direct, you can see we have a mobile phone here and we have a mobile phone here. So in addition to this direct link between this mobile phone to this mobile phone, what we can do is like, we can have RIS surface nearby those mobile devices. And this RIS device can ensure that, a signal reaches the other device with higher intensity. Okay. If suppose if it is made with, same phase. So what we can do is like, we can make sure that, it reaches the receiver and again, the CSNR will get increased. Okay. So these are all some of the use cases. So as I told, refraction, you can deploy it on the window and, whatever the electromagnetic waves that comes inside, okay, it can propagate through it so that users inside the home can have a proper coverage and connectivity. So this is other example, RIS for coverage. So you have a wall, so which is blocking the signal propagation from this access point to this mobile phone. So we are deploying an IRS or RIS so that this is ensuring that signal is reached to the destination. Okay. So channel redefining or interference suppression and so on. Okay. So this is a kind of setup which I found in a paper. Okay. So you can see here you have a transmitter end. Okay. With a transmit USRP or SDR, software defined radio, which is connected to the computer. And you can also see a transmit antenna, which is a horn antenna focused towards RIS. Okay. And again, here the operating frequency of entire setup is at 5.8 gigahertz. So something closer to, 6 gigahertz. And again, here you can see that there is another receiver antenna, which is connected with, receiver USRP and a computer. So what this setup they were trying to do is that they were trying to use RIS for reflection, and they are trying to make sure that, how the characteristics of the receiver signal looks like. Okay. And this is that surface. You can see this is the surface with totally 20 rows. Okay. 20 rows and 55 columns. Okay. So this is a setup. And recent days, there are several, RIS setups which are already available in market. Okay. Okay. So are there any questions? So until these thing whichever I have covered. Are there any questions? Please feel free to interact with me. So if you have any queries, you can also either, or drop in chat box, or otherwise you can ask. Okay. So I assume that, there are no queries as of now. So I'll proceed further. Okay. So, again, as I told, we have several use cases. Yeah, I got. Yes, no. Okay, fine. Thank you. Okay. So as I told, there are several, ways in which your RIS can be used. Okay. So one such is called as, RIS as a reflector. Okay. So this is this use case. So this is this use case. Okay. For coverage, we are trying to have this RIS. And also we will see how, it is reshaping the wireless communication system by providing better performance than, conventional setups. Okay. So that also we'll see during the simulation part. Okay. So this is how, this is a system model which was, investigated in a paper by Professor Basar. Okay. So you can see here a source with one transmitter antenna, and you can see a destination with one receiver antenna. And you can see an RIS surface, okay, Reconfigurable Intelligent surface with several elements. So here you can see this is one element, this is another element, and so on. Okay, so you have 4 rows. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 16 columns. Okay. So this entire, elements, that is 4 cross 16 forms the RIS surface. Okay. And here you can see that there exists a channel between the source and RIS element, which is defined as H. And similar way, the channel between RIS and destination is defined as G. And here I indicates that it is with the ith RIS element. See, for an example, the channel between source and the first RIS element is given as H1. Similar way, the channel between source and the second RIS element is H2. And the channel between source and, 16th RIS element is H16. Similar way, once after, if it gets, impinged on this RIS surface, what happens is that it gets reflected and it comes through some, space. So again, we can model that as wireless, channel fading as G. And again, here, I indicates, from which surface it is getting reflected. For an example, if it is getting reflected from the first surface, then this will be your G1. Similar way, if it is getting reflected from 20th surface, then this will become G20. Okay. So this is how the system model of RIS as a reflector will look like. Okay. So next to that, we will try to understand the received signal model for this RIS as a reflector, and we will proceed further with, detection and so on. Okay. So now let us assume you have some information which is X. Okay. And again, for all of these things, we will assume that, the transmitted signals are in the form of baseband form, which is Y equal to HX plus N. Okay. Where Y is the received signal, H is the wireless channel fading, and X is the transmitted signal, which might be from a QPSK or a PSK or QAM modulation, and N is your additive white Gaussian noise. Okay. So let us assume you have a source, and from this source, you are transmitting this X. Okay. X, maybe a QPSK symbol, or otherwise, it might be a QAM symbol and so on. Okay. So what happens is that this signal from the source is traveling towards your RIS, is getting reflected at the first RIS, and it comes back to destination. Okay. So now you can see that this signal, which is getting reflected from the first RIS and it is reaching the destination, comes across two channel fading. Okay. One is H1, which exists between the source and the first RIS element. The second one is your G1, which exists between your first RIS element and your destination. Okay. So again, from the first RIS element, so it is going to be H1 and G1. So we can model this in the form of two ways. Okay. So again, there are, two types of, system models that we can develop from this reflector. One is called as, intelligent one, and the second one is, your blind one. Okay. So blind one in the sense, we are not aware of, what is the phase by which, it is getting deflected, and, there is no effect, or, this RIS will never do any additional process to change the effect of the phase. Okay. So that's what, called as intelligent one. Whereas if it is, blind one, it just acts as a passive reflector, so that, whatever the signal from the source will fall on this and it comes here. Okay. So again, I have, two type of, equations for the system model. One is intelligent and blind. Okay. So I hope all of you understood the system model. Are there any doubts in the system model? Hope the system model part is clear. Okay. 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 So accordingly, the received signal can be written something like this. Okay. So y equal to square root of rho, summation from 1 to n hi exponential of phi I gi xj plus n. Okay. Where y is the received signal. Okay. Y is the received signal at the destination. N is the additive white Gaussian noise that is generated at the receiver side. Okay. And here you can see that we have a rho. So this means that, with some amount of energy, we will be transmitting our signal, or otherwise with some power, we will be transmitting our signal. So that power is denoted by square root of rho, which again indicates, some form of SNR, okay, average SNR. And next here you can see, HI indicates that, it is the channel fading coefficient between the source and the ith element. Okay. Similar way, GI indicates the channel fading coefficient between ith element and destination. And XJ represents the jth symbol of your modulation scheme. Okay. Or MPSK or MPM. So only thing that is left out is our exponential of phi I. Okay. So this exponential of phi I indicates that this RIS is intelligent such that it tries to do some form of, a phase adjustment or phase alignment, so that all the signal that reaches your destination will be having higher energy. Okay. So again, I have a simulation for this just to show, how this intelligent mode of RIS is highly beneficial compared to blind mode of RIS. Okay. So assume, it is like, you have this source, you are transmitting an information. So with some phase difference, it gets reached your RIS. Again, from here, it reaches your destination with some phase difference. So now what this RIS can do is, this can slightly adjust the phase of the reflected signal. So that adjustment of phase can be incorporated along this exponential of phi. Okay. So that all the signal that reaches your destination, okay, will try to induce higher SNR, so that, the performance of the system will be really good. Okay. So now next we'll try to understand why is this summation. Okay. Why is this summation? Okay. So let us assume you have a source, you are transmitting XJ. So now this XJ is getting reflected as the first element. It is reaching your destination. At the same time, what will happen? The same source which has transmitted XJ might reach your second RIS element, and again it will also get reached to the destination at the same time. So now if you see, you can see that there are 16 reflections from your RIS from this source to your destination. So again, all of them are getting collimated at the same time, or this gets reflected towards your destination, and all of that are reaching your destination at the same time. So due to that, what will happen? There will be a summation. See, for an example, you are transmitting from here to here, it is reaching here. At the same time, if something is getting reflected here and it is reaching here, what will happen? There will be a superimposition of the signals that is reaching your destination. So to make sure that superimposition is reflected on the received signal, we have this summation. This summation is mainly to ensure that, we have assumed the superimposition of all the signals.
ചിറ്റി നമ്മുടെ മകള് തറക്കുന്നതിനെ പറ്റി സർവ്വ സ്ഥലത്തിൽ ഇട്ടേക്കാണ്.
Excuse me, ma'am.
നമുക്ക്
Excuse me. Okay.
Sorry for the disturbance, sir.
Fine. Yeah. Okay. So, this summation makes sure that, all the signals that are getting reflected from the RIS is, superimposed or, reaching at the same time. Okay. So that's what that expression. So again, we can perform a detection using maximum likelihood principle. So which is nothing but a distance-based detection metric. So, I hope almost all of you know about this distance-based detection metric. So which is nothing but, see, for an example, you are having a BPSK symbol, okay, which is being transmitted. So the signal points of the BPSK symbol are either -1 and +1, which may correspond to 0 and 1, okay, to the bit 0 and 1. So now, if there is no noise introduced by the system, okay, so what happens is that at the receiver side, okay, your received signal also will be on the same signal point. Either it will be in -1 or otherwise it will be in +1. Whereas in the presence of noise, what will happen? Your received signal will not be on the same signal point, where it may be scattered somewhere nearby. Okay. So what we try to do is, okay, when you are transmitting a signal, you have a scattered point because of noise. So what we do is, from that received signal point, we try to find out what is the distance with respect to 1 and what is the distance with respect to -1. Okay. So whichever distance is minimum, we take it in favor of that. So that's what called as distance-based detection metric, which is called our maximum likelihood principle. So the same detection, okay, the same, distance formula is used here. So we have a received signal and certain things are assumed to be known. For an example, the channel fading coefficient is known well in ahead by channel estimation process. Okay. So this HI is known. And again, exponential of IA is known. GA is known. All of these things are known. So what we are interested in is we want to find out what is the symbol that is transmitted, whether the transmitter has transmitted 0, -1 or 1 or +1. So this is what our focus is. So our focus is here. Okay. So accordingly, we can use this ML principle and we can detect. Okay. So this is how the performance of, your RIS as a reflector, especially intelligent, will look like. And you can see the simulation results with SNR along the x-axis and BER along the y-axis. And you can see that, the performance of, 3 curves. One is with M equal to 2 and N equal to 2, and M equal to 2 and N equal to 4 and M equal to with N equal to. So here M equal to 2 represents BPSK, modulation number of BPSK. Okay, only 2 bits. Total number of bits possible is 2 bits. Okay. Similar way, N equal to 2 represents number of RIS elements present. So we saw some RIS element, right? So if suppose we are having only 2 elements, how will be the performance? So that's what this red line. Similar way, if we keep 4 RIS elements, how will be the performance? So this is what the blue line. And similar way, if you are having 8 elements, how will be the performance? So from this, you can understand that as the number of RIS elements are increased, the performance of the system is improving. That means less amount of BER we are able to achieve. So in other way, let us investigate at 0 dB. Okay, 0 dB. What you can observe is that this system M equal to N equal to at 0 dB is giving you, performance closer to 10 to the power -1. So this means that if you are transmitting 10 bits, out of that, 1 bit will be in error. Okay. So this means that, you are having more amount of error. Similar way, if M equal to 2 and N equal to 4, you can see that it is closer to 10 to the power -3. So this means that if you are transmitting 1000 bits, you may get 1 bit error. Okay. Oh, sorry. So here, 1000 bits, you may get 1 bit error. Whereas if you see this N equal to 8, what observation you can make is it is below 10 to the power -5. So let us assume 10 to the power 5. So if you are transmitting 1 lakh bits, only 1 bit will be in error. So this is the kind of, the performance improvement your RIS elements bring with increasing the number of elements. Okay. So it is better advised to have more number of RIS elements to the system. Okay. So that is one observation from this simulation results. Okay. So are there any questions? See, if I'm moving faster, you can also let me know, whether you are not able to understand and, I want to go a little bit slower. Is it okay?
Yes, sir. Please go ahead.
Okay, thank you. So next one is about, blind one. So as I told, RIS can, adjust the phase of the signal that is getting impinged on that. So some form of exponential of phi we saw in the received signal. Okay. So if suppose we don't have that exponential of phi, that's what our blind RA is. So just as a reflector. So whatever the signal that you're transmitting from the source, it goes and it gets reflected on the ith element and it is reaching your destination. So you have summation I equal to 1 to n, hi and gi, and you don't have any phase adjustments done by your RIS. Okay. So this expression can be written like this. And corresponding to this, we can also plot, write our maximum likelihood or detection principle using ML like this. Okay. And here you can see the performance of the system. Okay. So here also you can see that m equal to and n equal to, which indicates that we have used BPSK with m equal to, and number of RAS elements we are trying to increase. So here also you can see the same trend that as the number of RAS element is increased, the performance is becoming better. Okay, that is one strong observation we can make. So the other observation we can make out is, see, if you compare intelligent blind, what observation you can make is, see, at 0th dB, okay, at 0th dB, you can see that for n equal to 8, it is somewhere closer to 10 to the power minus 5. Okay, whereas here at 0th dB, it is somewhere between 10 to the power minus 1 and 10 to the power minus 2. So this means that when your RIS elements or the reconfigurable surface is intelligent, your performance is very much better compared to blind one. Okay, again it comes with certain complexity involved. Okay, so intelligent means you need to give some power. Okay, you need to estimate the phase by which it is getting received and reflected and so on. Okay, some kind of phase cancellation or phase adjustments has to be happened. Okay, in intelligent mode. The other system model is RIS as an access point. Okay, so this is like you have a source. Okay, and this source is very much closer to the RIS element. Okay, such that we were not able to differentiate a independent channel between your source and RIS elements. So that is a scenario for RIS as an access point. Okay, so this means that you have an antenna. Okay, and this antenna is having only limited amount of power, so that it can reach out to a destination, whereas it has a RIS element nearby that, such that this distance is so small between the source and RIS element, such that we were not able to differentiate to have a new or independent channel. Okay, so such kind of system. So there exists only one channel between your RIS element and the destination, that is G. Okay, and if it is from the first element, then it is G1. If it is from the second element, it is G2. If it is from the third element, it is G3, and so on. So accordingly, here we don't have any HI. Okay, so that is the only term that you cannot see in this received signal expression as well as the detection expression. Here you can see. So since we have this exponential of phi, it indicates that it is an intelligent one. Okay, it is not a blind one. It is an intelligent one. Okay, and we don't have this HI here. Rest of the things are same. So again, the detections, detection of the received symbol also you don't have HI, and remaining part are there. Okay, so now we will see the performance. So again, here also we have studied the BR performance. So now from this you can understand, right? Again, as the number of RIS elements, so which you can observe n equal to 4, 8, 8, you can see the performance is improving a lot. So how far is the improvement compared to the previous one, like a reflector? You can see for the previous one around 0 dB we had around 10 to the power minus 5 and 10 to the power minus 6, whereas for minus 4 itself we are having this. So this shows that if you have some provision to make use of RIS as an access point rather than reflector, it is advised to go for that. Okay, because it is improving your reliability or it is decreasing your bit error rate. Okay, that's the observation you can make out from this. Similar way, okay, if we don't have this exponential of phi I term with the received signal, which is mainly related to the phase adjustment brought down by your RIS, then it is considered to be blind RIS. Okay, so that we don't have this exponential of phi. And again, in the detection symbol also you don't have that. Now we will see the simulations. So here also the same trend we were able to observe. That is, as the number of RIS element increases, the performance is improving. Okay, this is the only trend we were able to observe. Now, if we compare this one with RIS as an access point and intelligent, this intelligent is going to be obviously better. Here you can see, right? 0 dB. It is somewhere near 10 to the power minus 1 and minus 2. But for minus 4 dB itself, it is much better. You can see it is between 10 to the power minus 6 and minus 5. Okay. So now, we will try to compare both the performances, like, reflector and access point. Okay. So from that, the observation is that, it is always advised to go with access point. Okay. If we have some provision. So this is like, see, you have, you are asked to develop a system model such that, you want to improve reliability. So the best option is, okay, to act as an access point. So this comes from the fact that in reflector, we have two channel fading coefficients between the source and destination for one RIS element. And again, they are getting multiplied. Whereas in the case of access point, we have only one channel fading coefficient between the RIS element and the destination. So because of these two channel fading coefficients which are getting multiplied, we are having, a poor performance compared to this access point. So this is, comparison with CISO. Here you can see we are comparing with CISO. CISO means you have a single transmitter and single receiver antenna. So from this, you can see that obviously your, RIS element with, n number of, like, n is equal to 8 and 4. Okay. It is obviously better compared to your CISO system. So this means that if you are having one transmitter and one receiver, okay, and if you are trying to transmit some information through them, between them, okay, you will get some BER. Okay. And again, if you are having an RIS element in between that, okay, without any direct line of sight. So this RIS element is obviously increasing the performance compared to your CISO system. Okay. So as of now, we have discussed about, RIS assisted communication where we dealt only with, one transmitter and one receiver. So now we will step into, single input, multiple output system, where we will have, one transmitter and multiple output antennas or multiple receiver antennas. So are there any questions? So there are any questions?
Excuse me, sir. Not a question, but a request.
Yes, ma'am.
Can you show that equation once again for blind RIS as access point?
Yes, ma'am. Yes, ma'am. Yes. So you want for reflector or access point, ma'am?
Access point.
Access point. Okay. So this is intelligent. You have exponential of Ia and Ga. There is no Hi.
Okay.
Okay. So correspondingly at the detection also, you don't have Hi. You have only exponential of Ia and Ga.
Okay.
Okay, ma'am. Whereas if it is a blind, you don't have exponential of Ia.
Okay.
Okay. Anyway, I'll share the presentation coordinators, ma'am. Okay.
Okay, sir. Thank you so much.
Okay. Are there any other questions? Okay, if there are no more questions, okay, I'll move forward. Okay, so now what we are going to do is like we are going to understand the system, RIS assisted communication system with a SIGMO setup, like, single transmitter antenna and multiple receiver antennas. So the system model may look something like this. Okay, so you have a single transmitter and you have a single receiver, and the single transmitter is having a single antenna, whereas the receiver is having NR number of receiver antennas. And in between, we have an RIS surface with N number of elements. Okay, and we assume that there is no direct line of sight between the transmitter and receiver due to some blockage. Okay, so due to some blockage. So now we need to first understand how will be the channel fading coefficient corresponding to this system model. Because earlier, for a CISO setup also, we have tried to understand the channel setup. Okay, so now we'll try to understand for the SIMO also. So as we have only a single transmit antennas, we will have a channel fading coefficient between this antenna and each of the RIS elements. Okay, each of the RIS elements. This means that H1 is between this, transmitter antenna and the first RIS element. Similar way, H2 is going to be between your transmitter antenna and second RIS element. The same way, H3 between transmitter antenna and third RIS element, and so on. So here we will have H1, H2, H3 until HN. Okay, HN. Again, the signal which is getting reflected from the first surface will reach the receiver. Okay, will reach the receiver in the sense it will reach all of the receiver antennas. So this means that, see, you have a signal which is coming from the transmitter and it is getting reflected from the first RIS element, and it reaches your destination or receiver to all the receiver antennas. So from this, we can understand that there will be NR number of channel fading coefficient between the receiver and the first RIS element. Okay. Similar way, from the second RIS element also, we will have NR number of channel fading coefficient. So like this, we have, NR cross N number of channel fading coefficient, where NR corresponds to the number of receiver antennas and N corresponds to the number of RIS elements. Okay. So now you can understand, see, at the receiver side, all these channel are going to be a vector form. Okay. All are going to be a vector form. So accordingly, we can write the system model equation like this. Okay. Y equal to square root of rho summation I equal to 1 to n hi gi xq plus n. And again, here we assumed that it is a blind one, since we don't have any exponential of I term or phase adjustment. So it is, blind one. So here you can see we have only hi, which is a 1 by 1, value, complex number. Okay, one cross one complex number. Whereas GA is a vector because we have NR number of receiver antennas. Okay, NR number of receiver antennas. And XQ is the Qth, transmitted symbol from MPSK or MPAM. So here Y is a vector because we have NR number of receiver antennas. So whatever the signal that is received at a time by the first antenna, let it be Y1, and the signal received by the second antenna, let it be Y2. The signal received by NR can be YNR. So that's why we can write it as Y1, Y2, Y3 as a vector form. Similar way, G1, I is the channel fading coefficient between the ith element. Okay, so I can be anything, 1, 2, 3, 4 up to n. Similar way, G2I is the channel fading coefficient between your second receiver antenna and ith element, and so on. So again, G also can be a vector of this form. And n is your vector of this form. Okay, all are like NR dimension. Okay, so earlier we were using only one transmitter and one receiver antenna in the previous system model. So we were having only an absolute operator. Okay, whereas now we were having, multiple receiver antennas. So now it is no more a singular, a 1 cross 1 complex number received at the receiver side, whereas it is a vector. So to address this vector, we will take norm operator. Okay, so this is a norm operator, and rest of the things are going to be the same, which has to be written based on your transmitted signal expression, Y minus square root of rho summation I equal to 1 to n hi gi vector xq plus norm square. That's it. Okay, so again, we need to perform, the theoretical analysis after doing this, system model. Okay, so because, why we want to do is like we want to validate our, theoretical analysis with simulation. Okay, so that's what we have done here. So what we have done is like we have used a pairwise error probability and union bound technique to find out average symbol error probability of the system. Okay, so if you take a simple digital communication system, okay, like a BPSK. So initially we have some BR expression, right, which is called as instantaneous BR expression. So the same thing you can see here, Q of something. Okay, let us assume Q of something, and we will try to interpret how it has come to this. Okay, so Q function is a generic one which we have seen from BPSK onwards. Okay, whenever we want to study the BER performance, we used to see. So the same Q function is there. Okay, but inside this Q function, we have certain parameters which are related to the system model. Like for an example, in digital communication, we don't have any channel H. Okay, because we model our digital communication system as Y equal to X plus N. That's all. Y is equal to X plus N. Whereas in wireless communication, what has happened? Y equal to square root of rho H X plus N. Okay, this means that you have some SNR, you have some channel H, and you have some symbol X. Okay, if suppose we use pairwise error probability, okay, then it can be written something like this. Okay, it can be written something like this with certain constant, like 1 by 2 rho norm of summation I equal to 1, n hi gi vector norm square d square p comma q. So this d square p comma q represents, okay, the distance between one symbol and the other symbol, or is a minimum Euclidean distance between one symbol and the other symbol of BPSK or QPSK or QAM and so on. Okay, and next, this is our expectation. See, why we are taking expectation is that, see, now you are having a system model. Okay, you have developed a system model. And at each and every time you have some channel. Okay. And this channel is not static. Okay. It is not a constant one. It is varying with respect to time. And again, it is completely random in nature. Okay. It is completely random in nature. So it means that, at one time, if you are running a simulation, you have a channel H. And the other time, if you are running a simulation, you will have a channel H2, H3, H4, and so on. So all are completely independent, and they are not static. It is random in nature. So now what we need to do is that we need to average it, because it is completely random. So if you want to find out the error probability, it has to be averaged. So that's why this expectation is here. Okay. And this is what that union bound technique. Okay. Summation Q equal to 1 to M and summation P equal to Q plus 1 to M. It indicates that we are taking into account all the possible symbols. See, this is like you have BPSK, right? Two symbols, X1 and X2. Okay. X1 and X2. So here, what are the two possibilities of error can happen? One is the transmitted might be X1, but you might have received as X2 or detected as X2. Similar way, the transmitted might be X2, but you might have detected as X1. So we are trying to take all possibilities. The same thing applies here. But see, for an example, again, if you want to take QPSK, there are 4 symbols. Okay, 4 symbols. X1, X2, X3, and X4. Okay. So if suppose we assume you are transmitting X1, there are chances that you may detect as X2. There are chances that you may detect as S3. There are chances that it may detect as X4. So with respect to one symbol point itself, we have, several possibilities. So all these possibilities will be taken into account. So that's what you can understand here. When summation Q equal to 1, okay, P runs from 1 plus 1, 2 to 4. If it is QPSK, okay, 2 to 4. Similar way, when it is 2, then we are taking 3 to 4. So from this, what you can observe is that some possibility we are avoiding it. So which is a recursive or recurrent. So due to that, we have kept 2. Okay, so this is how this expression. And Q is a standard Gaussian Q function. Okay, E is the expectation operator, and so on. Okay, so see, from this, we got motivated how to develop a low complexity detector. So this is the expression from which we got motivated. Okay, how to develop a low complexity detector, so that from this we have understood. Why? Because see, we know what is Q function, right? What is the Q function? Q function is a standard Gaussian Q function, right? Okay. So how is our Gaussian function? It is a bell curve. Okay, bell curve. It is a bell curve, something like this. Okay. And again, what is the total area of this bell curve? The bell curve total area is 1. Okay. The total area of the bell curve is 1. Okay. So now if we take from half, that is 0 midpoint. Okay, 0 midpoint. If we take for half, what will be the total area? Half. Okay. Similarly, if you move away from 0 towards the right side, okay, like again the positive side, if you move away from origin along the positive side, it means that you are increasing your x. Okay, you are extending your x. And again, if you're checking the area from that x, which is slightly deviated from 0, you can observe that again the value is going to be minimal. So this means that the total area between minus infinity to plus infinity of a Gaussian function is 1. Whereas the total area from 0 to infinity is half. And again, if we take any point greater than 0, and from that point to infinity, that area is going to be again smaller. So this means that whenever the argument of your Q function is larger, okay, larger, your output is going to be smaller. Okay. So this means that if you see, what's our objective in general? If it is reliability, what is our objective? Our objective is to reduce this. Okay, our objective is to reduce this. So especially if you take this expression, which parameter will help us in reduction is, if this argument of the Q function is larger, then this will become smaller. If suppose this argument is very smaller, what will happen? This will become larger. Okay, so this is the key idea based on which we have developed, our system model, low complexity detector. Okay. So our motivation is from this. So we got this Q function, and from this we understood that it can be improved. So what we thought of doing is we used this Q function, and from that we tried to minimize the error probability. And again, as I told, we want to reduce the complexity involved. So how we have reduced the complexity is that see, as you have seen in the previous system model, we were having several number of antennas, right? Several number of antennas. So all these antennas will have some low noise amplifier, then, some kind of, mixer and RF synthesizer, phase synchronization, and so on. Similar way, if you are having NR number of receiver antennas, we are having NR number of such RF components. So which will always drain more amount of energy. Okay. So to avoid that, what we have proposed is we can have some generalized selection combining scheme, where instead of using all the NR receiver antennas, we will use only certain number of receiver antennas for reception purpose. Okay, that's a low complexity detector we have proposed. Okay, so with that, if possible, we will move ahead with the same direction, or otherwise, I'm ready to show some demonstration using MATLAB for whatever the system model I have shown. So if there are any questions, I'm ready to take.
Participants can share their questions in the chat box or raise your hands. So we will unmute you. If there is any questions in between, you can share in the chat box.
Yes, participant can share your views. See, again, from this, I can take it in two directions. One is I can show the system model which we have developed and which has got published in IEEE MapCon. Okay. Or otherwise, what I can do is like I can show the demonstration of whatever the system model I have discussed so far, like RIS as a reflector, RIS as an access point, and so on. So so participants can share your views so that accordingly I will take it forward from here. Okay, is there something in the chat? How to maximize the argument of Q function? Yes, very good question. So how to maximize this argument of the Q function? Yeah, so, see here, this anyway, this is the argument, right? Whatever is there within the braces of the Q, that is whatever argument. Okay. So here in this argument, some of the things are constant. For an example, 1/2 is a constant. Okay, rho, which is SNR. Okay, rho, which is SNR. This means that this is related to the transmit power. So again, under this also, we don't have any control. Okay, we don't have any control because we are designing a receiver. Okay, and this receiver doesn't have any control over the transmitter because the transmitter will fix certain power and it is transmitting it. Similar way, D square P comma Q. So this is the distance between two signal points of a constellation. Let us assume if it is BPSK -1 and +1. So what is the distance? Distance is 2. So 2 square 4. So again, this is a constant. Similar way, if you take QPSK 0.707 plus J 0.707, 0.707 minus J 0.707, and so on. Again, all the signal points are fixed if we fix the modulation order. So again, this is going to be a constant. So only parameter we can play around this using this terms which are present inside the norm function. Okay, which is summation I equal to N HI GI. Okay, so that's how we can maximize. Did I answer to your question, ma'am? Okay, thank you. Okay, so what I will try to do is then I will show the presentation related to the updated work. Okay, from this RIS assisted communication, that is low complexity detector, and if time permits, I'll show one demonstration or MATLAB demonstration so that you may be able to understand how to develop a system model. Okay, and how the model is developed and so on. Stop sharing now. Share on the screen. Okay, so this is the system model we have proposed. Okay, and this is the title of our paper. So performance analysis of RIS assisted CMOS system with generalized selection combining. Hope the screen is visible to all.
Yes, sir. Yes, sir.
Thank you. Okay, so So idea behind the proposed system is this Q function. Okay, so the same CMO, okay, same received signal expression. Okay, and this is our signal, and this is a Q function. Okay, so now we all know that, right? Selection combining, which is a technique used in CMOS system or MIMO system. Okay, where the operation is that we will have several. Let us assume we have 4 receiver antennas. Okay, 4 receiver antennas. So in selection combining, what we try to do is like out of 4 receiver antennas, we will choose one antenna. Okay, we'll choose one antenna. Okay, maybe you can choose 4th antenna. Next time you can choose 2nd antenna. You can choose 3rd antenna, 1st antenna, and so on. So you can choose any one antenna. So that's what called as selection combining. If it is generalized selection combining, we have the freedom to choose any number of antennas. Okay, any number. Like for an example, out of 4, you can choose any 2. Okay, 2 antennas. 2 you can choose at a time. The next time you can choose other 2, or the other you can choose 1 and 2 you can choose, or 1 and 3, and so on. Okay, or otherwise by the next time, if you want to configure it for 3 receiver antennas, you can choose 3 antennas and so on. That's what called as generalized selection combining. Okay, so now we understood that the only possibility to improve BER is by increasing the argument of the Q function. Okay, increasing the argument of your Q function. And again, under that, we understood that there are certain parameters on which we don't have any control. Like, rho, we don't have any control at the receiver side. 2 is constant. D square Q comma P is also constant. So on that also, we don't have any control. So only parameter we can play around is with this term, HI and GI vector. Okay. So now let us assume, you have a transmitter. Let me check. Yeah. So you have a transmitter. Okay. You have several receivers. And you have several, channel fading coefficient between all of these receivers with respect to ith element. Okay. So now what we need to do is, we need to choose a particular receiver antenna. Okay. Particular receiver antenna, which will maximize this function. Okay. Which will maximize this function. Okay. So that let us assume, assume you have 4 antennas. Okay. You have 4 antennas. You are having some channel fading coefficient. And that channel fading coefficient is giving us some channel gain, which is here it is 2, here it is 4, here it is 0.5, here it is 0.25. So now from all of this, what we can infer? We can infer that first antenna is giving 2, the second antenna is giving 4, third one is giving 0.5, the fourth one is giving 0.25. So which channel gain is more? The second channel gain is more. Okay, this means channel gain is nothing but, magnitude of H1, magnitude of H2, magnitude of H3, magnitude of H4, and so on. Channel fading coefficient means H1, H2, H3, H4. Like all of those complex coefficients are called as channel fading coefficients. The magnitude of that's called as channel gain. Okay. So now given these 4 antennas, if I ask you, please choose any one antenna. Which antenna we will choose? We will choose the second receiver antenna because that is the antenna which is giving higher gain. So this will give us Q of square root of rho by 2 magnitude of 4 square times D. Whereas if you take the first antenna, what will be the Q function? The Q function will be Q of square root of rho by 2 magnitude of 2 square, or this is not 2 times D square Q comma P. Whereas if you take the third antenna, it will become Q of square root of rho by 2 norm of H3, which is 0.5 D square QP. Same way, if you take 4th antenna, it is going to be Q of square root of rho by 2, 0.25 times D square QP. So now if you see all of these Q functions, which Q function will give us less error probability? The second one, because it has higher channel gain, which is 4. Okay. So this is the principle based on which we have developed our generalized selection combining. Okay. So accordingly, what we will try to do is we will try to find out all of these channel fading coefficients and its gain with respect to each of the receiver antennas, and whichever antennas, like for an example, if I have the flexibility 2, so which of the 2 antennas which are giving maximum channel gain, I will choose that. If it is 3 out of 4, then which of the 3 antennas are giving maximum gain, I will choose that. Okay, so that's what V1, V2, VNR or some antennas. So accordingly, once after we choose it, we have only, small NR number of receiver antennas. So this small NR represents number of receiver antennas through which we are going to receive the signal. So that's what our small NR. Okay, small NR. So here you can see VY1, VY2, and VNR. Okay, so NR number of receiver antennas. See, if it is SIMO, we will have, if it is 4 antennas, we will receive through all the 4. Whereas if it is with the selection combining, then we will have, limited number of antennas. Like, 1 antenna, you can choose 2 antenna or 3 or 4. So again, the detector will look something like this. Okay, distance-based detection or ML detection. You'll have something. So coming to the performance analysis, again, we have the same Q function, okay, which can be represented something like this. Okay, so now already we have seen, right? We have this expression. Now we want to average this. This is only an instantaneous BER or instantaneous symbol error probability. Okay, so we want to average this. Okay, so again, when you want to average this, what we need to inspect inside is we want to inspect what is the random variable present inside. Okay, if you see the Q function, you can see that rho is a constant, 2 is a constant, d square q comma p is constant. So all of these are constant. So only thing that varies with respect to time is norm of summation I equal to 1 to n hi g vector v comma I square. Okay, so this is the only term that varies with respect to time. So what we need to do is we need to find out what is the probability density function of this function or this random variable. So once we know this random variable PDF, what we can do is like we can average it. See the conventional formula. If you have expectation of AX, let us assume A is a constant and X is a random variable. What is the formula? The formula is A expectation of X. Am I right? So the same thing we will do. And again, we know the expectation formula, right? Expectation of X for a continuous random variable. How do we use to write? We will write it like, expectation of f of X is equal to integral minus infinity to infinity x fx of x dx. This means what we are trying to do, we are taking the function and we are substituting the PDF of the function or the random variable and we are integrating over the limits minus infinity, infinity. The same thing we are going to do. Okay. So by literature, okay, it is known that, if you have one transmitter antenna and one receiver antenna and one RIS element, or n number of RIS element between them, this particular channel fading coefficient, okay, which is given here, will have a PDF, something like complex normal with mean 0 and variance n. Okay, mean 0 and variance n. Complex Gaussian random mean 0 and variance n. So this means that you have one transmitter, one receiver, and n number of RIS elements. Okay, n number of RIS elements. So for this, the channel fading coefficient is something like this. Okay. Again, we assumed the Rayleigh fading for this. Okay, Rayleigh fading. So the PDF can be found out something like this. Okay, this is a PDF. Okay, again, which can be found in some literature or some research papers. You can see that. So next, what we have done is we have this Q function, right? We have this Q function. So there are several alternate expression for this Q function. Okay, because usually Q function is a integral form. Okay, just not in closed form expression. So what you can do is we can use any alternate integral expression for Q function. Okay, so one such alternate integral expression for Q function is this. This is one such alternate. So if you are using that in that Q function, you will get something like this, and you can substitute the PDF. So this PDF, and if you integrate, you will get it in the form of single integral expression at first, and later again, if you are integrating it using some books, like table of integrals, you will get it in closed form. Okay, so this is how the error performance is done. Theoretical study is done. So in addition to that, what we have done is like we also have studied the outage probability. Okay, so what is the probability that whatever the receiver antenna you have chosen is under outage? So by definition, outage indicates that already you are having some SNR, received SNR. When this received SNR is going below certain threshold, it is called as outage. Say, let us assume you have a transmitter and you have a receiver. Okay, let us assume the instantaneous SNR is gamma. Okay, gamma. If this gamma is lesser than certain threshold, like gamma TH, then we call that as outage. So here we have this gamma, rho gamma less than gamma TH. So that's what we have. So already we know the PDF of gamma. So if you are integrating over the limit 0 to gamma TH by rho, you will get this outage probability expression. Okay, so coming to the simulation results for this work. So again, here we have plotted the performance theoretical and simulation results in terms of average symbol error probability. So along the x-axis, you can see that it is SNR, And along the y-axis, it is, average symbol error probability. And you can see that, different legends with, caption SIMO RAS GSE, which means that single input, multiple output with reconfigurable intelligent assistant surface and generalized selection combining. Okay. And here 4,32,1 indicates we have assumed 4 receiver antennas, 32 RAS elements, and out of which, and again, only 1 receiver antenna out of 4 receiver antennas is used for signal reception. Okay. So there are 4 antennas, but I'm going to choose only 1 for signal reception and decoding. And this is for simulation and theory. And this is for, 2 antennas will be used, 3 antenna and 4 antenna. So this system, like 4,32,4 marked with magenta color, indicates your performance of SIMO RAS. Okay, SIMO RAS. Okay, whereas this one, this red indicates, selection combining. So blue and, brown indicates, generalized selection combining with the 2 antennas selected out of 4, 3 antennas selected out of 4. So from this, you can observe that when we increase the number of RF chains or the provision to choose 2 antennas compared to 1 antenna, you can see there is a good amount of performance improvement, like, greater than 2 dB. You can see here at 10 to the power minus 4. If you see, it is somewhere closer to -6, whereas here it is -4. So this indicates that, when we are increasing the number of antennas chosen from 1 to 2, the performance is increasing by 2 dB. Whereas from here, you can see that, the performance is not that much significant, but obviously there is some small performance improvement. Okay. So same way, if you see, 3rd and 4th, you can see that, it is more or less closer. Okay. So this is the observation we were able to make out from this figure. And another observation we can make out from this is that, almost all the curves have same slope. Okay. If you draw a slope, what you can see is like, you can draw a line, something like this. Again, you can draw a line, something like this, something like this, something like this, and so on. So if you draw a line, we can observe that, all the lines are going to be parallel. Okay. All are going to be parallel like this. Okay, all are going to be parallel like this. Okay. So that is not. So this indicates that it is giving us some same diversity order, because diversity order is a crucial parameter whenever we try to understand the performance of the system. Okay. So diversity order. So from this, we understood that the diversity order for our SIMO RAS GSE is number of receiver antennas. See, for an example, even though you are having 4 receiver antennas and you are choosing only 2 antennas, you are able to get the same diversity order as 4. Okay, so that is another observation. So I can see something on the chat. Okay. Okay, so, this is the slope. Okay. So we have a formula for finding out the slope, right? M equal to y2 minus y1 by x2 minus x1. The same formula is applied here. Okay. But instead of, instead of our conventional geometric based analysis, we have kept it in the form of, logarithmic scale. Why? Because, we have here in the form of dB scale. Okay. So that's why we have used. So you can see for SIMO RAS GSE 4,32,2. This means you have 4 receiver antennas, you have 32 RAS elements, and you are choosing 2 antennas for reception. Okay. And at -6 dB, okay, -6 dB. So somewhere here, okay, you can see that the performance is somewhere closer to 10 to the power -4 and 10 to the power -5. So which is 7.04 10 to the power -5. Similar way, at -2, you can see that it is somewhere between 10 to the power -5 and 10 to the power -6. So which is 1.8 into 10 to the power -6. So substituting these values here, and by using the same formula like y2 minus y1 by x2 by minus x1, we were able to get the slope as 3.98. Okay, which is nothing but 4, which is nothing but our n. So from this, we can infer that even though we choose certain number of antennas, okay, like, 1 antenna or 2 antenna, we were able to attain full diversity. Okay, we were able to attain full diversity. Okay, so this is, for a different configuration. As the number of RAS elements is increased, how is the performance? Okay, number of receiver antenna is decreased, what happens? So here you can see, this is for 2 receiver antenna. Okay, red color, 2 receiver antenna, 32 RAS element, only 1 is chosen. So for this one. So here also you can see that the diversity order is 2. That means total number of receiver antennas. Okay. So more and more the number of receiver antennas, more and more the performance better is. More and more the RAS elements, more and more the performance is improvement. Okay. Similar way, if the number of RF chains is increased or number of receiver antenna chosen is increased, there will be only a slight marginal improvement. Okay. So these are some of the observations. So from this, what we understood is that, as the number of RF chains is increased, the performance is improving substantially when we increase from 1 to 2. Whereas beyond that, the performance is not that much significant. Second one is, we were able to reduce the computational complexity involved. Like, we were using only few antennas and also, few RF links. So that will make sure that, less computational complexity is involved. And again, we have found out some theoretical symbol error probability and outage probability and diversity order also we have found out. Okay, so further we were planning to extend this for a setup with multiple RAS. So here we have considered only one RAS board, right? Similar way, what will happen if suppose we have multiple RAS boards and if we extend the same system to different use case with active RAS and simultaneous wireless transmission and power transfer and so on. So these are all some of the future works we have planned. So any queries, you can drop an email to me, okay, or otherwise to my students. I hope they will respond to your emails. So better to drop an email to me, okay. So I'm ready to take some questions because we have only 5 minutes more.
Participants can share your questions in the chat box or
Yes,
raise your hands using raise hand button. So we will unmute you.
Yeah, please. There are any questions?
Sir, have you tested this in the lab?
No, sir. No, sir. We have done some MATLAB-based simulation, sir. Because we don't have the setup. Because the cost of RAS element, for setting up, it is somewhere around 29 lakhs.
Oh.
Okay.
Okay,
So we have not tested it, sir. It is based on, simulation study. Simulation and, theoretical study.
Okay, thank you.
Thank you.
Participants are requested to share your doubts, if any.
So,
Sir, on behalf of the Department of Electronics and Communication Engineering of Jyoti College, and behalf of all our participants, I extend our heartfelt gratitude to Sir for this truly enriching session. Thank you, Dr. Anand Sir, for a focused and comprehensive session on RIS assisted communication.
there is some.
Complemented the morning discussion and added significant depth to the participants' understanding and intelligent surface technologies. The system design and performance perspectives you presented will be a valuable reference for a faculty exploring research in this area. Sir, we wish you all the best in all your future endeavors, and we hope to have the privilege of your presence and guidance again. Thank you very much, sir.
Sure, ma'am. Sure. There are a few questions, ma'am. One is, sir, you experimented with an NR value of 4 only or some other? Ma'am, we have experimented with different values, ma'am, like, 8, 4, 6, then 2, and so on. So we have done some, experimentation or simulation with the different values. And sir, which are research areas suggested for UG students? So right now there are, a lot of research scope in wireless communication because, 6G, 5G, all of these things now have opened several scope for improvement. Because recent days you can see we have integrated sensing and communication. So what we can do is like separately, first we can understand the system model of RIS and integrated sensing and communication. Later, if you want, you can bridge both of that together so that, we can improve or, achieve any one of the requirements of wireless communication system. See, finally, whatever the system model we develop, it has to suit in some point of, requirement. So that is the key thing. So integrated sensing and communication we can have, or otherwise we cannot. Recent days you can see data-driven communication approaches there, like using deep learning, machine learning for our wireless communication, especially for channel estimation, then signal detection, and so on. And especially for our RIS based, there are certain challenges associated. The challenge is that channel estimation will be a big problem, because we were saying that we were having 32 RIS elements, 64 RIS elements. So finding out the channel fading coefficient between the transmitter and receiver with respect to each and every RIS element itself is challenging. So what normally they do is they try to find out with respect to certain RIS elements, and later they try to interpolate, saying that these channels are correlated. Okay, see, all of the assumptions we have assumed is like independent. Okay, but normally in principle they do that only to certain elements they will try to find out the actual channel fading coefficient. With the rest of the things they will try to interpolate. So that's how they do. So there are a lot of problems. So that's all from my side. So again, from my side, I thank the coordinators for giving me this wonderful opportunity. And also I thank the administration of Jyoti Engineering College for giving me this opportunity. Thank you all. Thank you very much.
Thank you,
dear
sir.
participants, for your time.
Thank you, sir. Thank you so much.
Thank you, sir, for accepting our invitation, sir. And it was a wonderful session.
Thank you. Okay, so may I leave, ma'am, sir?
Yes, sir.
Okay, okay. Thank you, ma'am. Thank you, sir. Thank you. Thank you.
Thank you so much. Bye-bye.
Thanks.
We will resume our FDP on 15th June at 10:30 a.m. Have a great weekend. Okay. Thank you all.
The recording has stopped.